Welcome everyone. Let's do this question. State the effect of the spatial filtering kernel shown in figure Q2a would achieve. If you take kernel number 1, you can see all the entries are 109s. If you take an image and place a kernel somewhere on the image, what would happen is the underlying pixels would be multiplied by the entries on the kernel in the kernel, and they will be summed. So you can see under this window, there lies 9 pixels 3 by 3. So what this means is all these 3 by 3 pixels will be added and be divided by 109. So you can say this is the averaging kernel. A second one, as you see, have all minus ones in the top row. In the bottom row, all plus ones. So we know when a kernel is run, the structures in the image that are similar to the structure of the kernel get sort of amplified or intensified. So therefore, if you locate an image in this fashion, for example, assume that these pixels underlying are dark and these are bright. So dark pixels are 0, bright pixels are 255. That underlying image will tend to give a high value at this point because the image looks like the kernel. So therefore, you can see this is from dark to bright transition. So therefore, this is a horizontal, it's a horizontal edge that is detected. It's a vertical gradient kernel. Or horizontal, detects horizontal edges. Similarly, this kernel, as you see, would respond highly for an image like this. Dark pixels in this region, bright pixels in this region. So therefore, this kernel would be horizontal gradient kernel. Detects vertical edges. Now this kernel, if it were like 0, -1, 0, -1, 4, -1, 0, -1, 0, it would have been a blob filter. But since this central entity has become 5, we know that it is a sharpening kernel. Okay. So let's look at part B. Figure Q2b shows an image, a kernel, and a grid for displaying the output. Apply the edge detection operation on the image using the kernel shown in the same figure. Show the output in the given grid. So here we have to realize that if we take this as a center of the kernel, it is a center of the kernel, and locate it here, the kernel overlaps the image in this fashion. The numbers will get multiplied by the numbers in the kernel. So 10 multiplied by -1, I just write the entry there. This by -2, and 40 by -1. So at this location, the number that you get can be calculated by summing all these numbers in the image multiplied by the values of the kernel 0, 0, 0 and 1, 2, 1. So a little bit of a manipulation to do there. The answer would be 200 plus twice 190 plus 180 minus 10 minus 2 times 20 minus 40. Let's do that calculation. $670. Then the kernel has to be moved to the right. So we are looking for the value over here. So kernel will be stationed over there. So minus 50, minus 100, minus 170, 200, plus 2 times 220, plus 200. So this is the answer that you would get there. I hope these numbers are correct. 520. So then you move the kernel over here and get the value there. Kernel over here and get the value here. Kernel over here, get the value there. And kernel over here and get the value there. So since the kernel cannot fully overlap at any other location than these 6 locations, these values do not get numbers. Then in the max pooling operation, apply 2 by 2 max pooling operations tied 2 on the result. So for the max pooling operation, what we have to do is locate a 2 by 2 window. So let's locate 2 by 2 window on these entries that are valid and get the maximum value of that. So let's consider this as the 0, 0 location of the kernel that's where the value resizing. So take the maximum value out of all these entries. So I cannot do it right now because I did not put all these values. Get the maximum value. Take the maximum value and put there. Now, since it is stride 2, and that's all we can do right now because it's stride 2. It has to go and be located here. So we cannot do anything. So that's all. Okay. Question part C. Figure 2C shows a part of an unnormalized 3 by 3 Gaussian kernel with sigma equals 2. Fill the other entries in the kernel. So since we had to do the unnormalized version, we have to take the Gaussian. Sorry about that, gxy as, we don't have to write the normalizing constant, e to the power of minus x squared plus y squared divided by 2 sigma squared. So let's first verify that, let's compute this number first. So for this number, x is equal to xy is equal to 0, 0. So g00 would be equal to e to the power of minus 0 plus 0 divided by 2. Sigma is 2 times 4. Anyway, e to the power of 0 is 1. Then let's compute this entry. So there you can see x and y. When the x is 0, y is 1. That's our convention. So G01 e to the power of minus 0 plus 1 divided by 2 times 4. We had to compute that. Sorry about that, not being able to do the calculation quickly. Actually, my hands are tied with the computer, that's the problem. 0.8825. Yes. So you can see by symmetry, this is also correct. So now we are sure that our calculate manipulations are working. Then let's consider this number. This is g minus 1 equals e to the power of minus 1 divided by, sorry, we have to square them. So 1 plus 1 divided by 2 times 4. Zero 0.7788. I hope this is correct. So this same number will go there. You can see by symmetry, you get this because it's x squared plus y squared. And this same number goes here, 0.8825, 0.8825. Okay. Now compute the normalized kernel. To compute the normalized kernel, what we had to do is sum all these numbers. That means 1 plus 0.7788 times 4 plus 0.8825 times 4. That's the sum of that, and divide the kernel with that. So let's do that. 7.6452. So to compute the normalized version of this, we have to take 1 over 7.6452. And to compute this corresponding number over there, 0.8825 divided by 7.6452. And to compute the corresponding number for this, we have to do 0.7788 divided by 7.6452. So what you have to do is do these computations and show the normalized kernel. So let's do one of them. 0.1308. 0.1019. 0.1154. So you know that these entries will have to be reported. Why are all the 9 entries nearly the same? because sigma is large for a 3 by 3 kernel. So we have seen that the half width of the kernel must be at least 3 times sigma usually, right? I mean, this is maybe too large, gives a too large a kernel, but this is the condition. Consider an image with several types of coins. How can a spatial filtering approach be used to detect the type of each coin? So the image may be a coin like that, maybe a coin like this, different kinds of coins, a coin like that, you know. Yes. So we assume that the shapes are different of these coins. So what we had to do is to take the templates of those coins and consider this as the kernel and then carry out filtering. Extract a template for each type of coin, and then secondly filter the image with each of these templates. So these are the kernels. Then non-maximal suppression, because a lot of points will have high values when you filter using a kernel like this. So you have to do non-maximal suppression to select one point among this hill kind of a structure. Okay, thank you.